Okay, welcome back. So today I'm going to talk about the micrometer screw gauge. Like the vernier caliper that I discussed in the last video, the micrometer screw gauge is also an instrument used to measure the length. Micrometer screw gauge can be used at various occasions, and let's find out about some details about the micrometer screw gauge and and as to how we can take the measurements using the micrometer. So to introduce with, we need to identify what is a micrometer screw gauge. So you can see in this picture that the micrometer screw gauge is a fine threaded instrument. You can see these threads here. When I rotate this screw or even this screw, these threads will go from this part. I will explain about the parts later, and you can take the measurement. You can increase the length of this shaft like rod. I'll explain the parts. Shaft like rod, you can decrease it, you can place the object, and you can take measurements. So as I mentioned in the video on vernier caliper, what are the advantages and disadvantages of using a micrometer screw gauge, and when can we use a micrometer screw gauge? So that those will be the next questions that I have to answer you. So micrometer screw gauge is a very fine and a very smooth instrument. Unlike the vernier caliper, these two points of the micrometer screw gauge, so this gap is the gap that we are using to keep this object. For example, if you want to measure the length of the width of a coin or the width of some papers, right? We keep those papers or the coins here and then measure the length. However, unlike the vernier caliper, the micrometer screw gauge doesn't exert too much pressure on the object. So micrometer screw gauge is ideal for taking measurements in which the pressure is not important. For example, if you want to take the measurements of some brittle objects, for example, you want to take the width, you want to measure the width of a rubber strip or some papers, using a vernier caliper, sometimes the rubber may deform, or sometimes the papers, there may be errors in the actual width because of the high pressure exerted by the vernier caliper. But when using a micrometer screw gauge, you don't exert, these two rods don't exert a pressure on the object. So micrometer screw gauge is ideal for taking measurements of brittle objects. Furthermore, micrometer screw gauge has a very fine measurement system in which it is much sensitive to measurement than when using a vernier caliper. However, there also exist disadvantages of using a micrometer screw gauge. One of the greatest disadvantages being that the micrometer screw gauge, like other measuring instruments other than the vernier caliper, cannot be used to take internal measurements. For example, if you want to measure the width of some object, you can't use a micrometer screw gauge for that. Also, if you want to measure the depth of an object, you can't use it. So there are various advantages and disadvantages. So let's go deeply into the topic of micrometer screw gauge by identifying its parts. So here's a sample of a micrometer screw gauge, and I have named these parts. So let's find out what are these parts and why these parts are necessary in order to take measurements. So identifying parts are very important before understanding about the methods of taking measurements and the various types of measurements that can be taken. So first of all, there are 4 or 5 main parts that are necessary for the micrometer, and some other parts are actually not necessary but may be necessary at various occasions. For most of the measurements that you take using a micrometer, the anvil, the spindle, the sleeve, the thimble, and the ratchet are the most important parts. Actually, the baseline or the main scale and the micrometer scale can be seen in any micrometer, and those are necessary to take measurements. But the most important physical parts are the anvil, the spindle, the sleeve, the thimble, and the ratchet. So what is the anvil? Alright, when you keep an object here, for example, if you want to measure the width of some ball, a very small, say, lead ball, right? Lead ball that you use in some practicals in heat and the other topics that are covered under physics. you want to measure that width, what you do is that you rotate the spindle in this direction, so that this spindle, now when you rotate this ratchet in this direction, the spindle would go inside this. Now this is like a hollow tube, but the ratchet is connected here, so the spindle will go here and you can keep the object here. So this is very similar to the fixed jaw of a vernier caliper. So it's always better if you can compare the different parts of a vernier caliper with that of the micrometer. So the anvil acts like the fixed jaw of a vernier caliper, in that it's fixed to this frame, and when I rotate the ratchet here, the spindle goes here, you can keep the object, and you can rotate the ratchet the other way, so that the spindle now goes in this direction, and you can keep the object in contact, right? And the spindle, now I explained to you that the spindle is important to keep this object in contact with the anvil. And the sleeve, in which we can see the baseline and the main scale, is like the fixed part of the vernier caliper, right? This is fixed, this doesn't move. And the thimble is the vernier scale, thimble with the rotating vernier scale. So this is very similar. Micrometer screw gauge is in most aspects very similar to the vernier caliper. So we have a main scale here, we have a rotating vernier scale, like now in the vernier caliper we had a vernier scale in which we can move in this direction or this direction, that is in the x-axis. But in the case of the micrometer, it's like the y-axis, we are moving vertically, not horizontally, in this, not in this direction, in there, right? Either clockwise or anti-clockwise. What actually happens when you rotate this ratchet is that this thimble with the rotating vernier scale rotates here, and you can see different parts of the sleeve when it is exposed. So that I'll explain you in the next few slides and in the next few minutes. So the micrometer scale is seen on the thimble, and the mainline and the baseline is where you can see is actually the coincidence point. Now I explained to you in the concept of vernier caliper also about the coincidence point. The point in which the rotating vernier scale and the main scale coincides is called the baseline. So baseline is important to take measurements, and in the vernier caliper, it's also important to determine whether there is an error in the micrometer. So those are about the key parts of a micrometer. Now, as in the case of the vernier caliper, let's identify some special definitions on micrometer measurements. Unlike the vernier caliper, micrometer has a special definition called a pitch. A pitch of the screw is the distance moved by the spindle per revolution. Now in this diagram you saw, when I rotate this 360 degrees, this will rotate here, and the sleeve will be exposed in this direction. And when I rotate the ratchet in the other direction, this thimble will rotate this side and the sleeve will be hidden. So when I rotate this ratchet 360 degrees or one revolution, the distance that the spindle moves is called the pitch of the screw, or pitch of the micrometer screw gauge. However, the pitch may vary for different micrometers. Now you can see some micrometers where there are 100 parts, 100 vernier parts. So you can see that somewhere you can see 100 vernier parts in the vernier scale. Some micrometers you can see 50 parts. So the pitch of the screw varies for different instruments. So you need to identify what is the pitch, and that's important in calculating the least count. So least count is the pitch divided by the number of divisions on the circular scale. Now as I explained in the theory of vernier caliper, least count in the vernier caliper was equal to one vernier scale division divided by one main scale division, one main scale division minus one vernier scale division. And in the case of the micrometer screw gauge, least count is equal to the pitch divided by the number of divisions on the circular scale. Now as although I told you about this series, it might be confusing to you, so let's go for an example. So if you are given a micrometer of say 100 equal divisions, and if the pitch The distance traveled by the spindle per revolution is 0.5 millimeters. The least count is equal, from this formula you can say pitch divided by the number of divisions on the circular scale. So the pitch has been given as 0.5 millimeters. Number of divisions on the circular scale is the number of parts, small parts you can see on the vernier scale or the circular scale, or sometimes it's called also the auxillary scale. I will use all these words in the next few slides. On the circular scale is 100 equal divisions, so the least count is equal to 0.5 millimeters divided by 100, which is 5 upon 1000 or 0.005 millimeters. So that's about the least count. Now, having explained about the least count and the pitch of a micrometer, let's find out as to how the length formula for a micrometer can be built up and how the length of some object can be found using a micrometer. Although the least count may vary, and although when the least count varies, actually the pitch also varies. So both the least count and the pitch may vary for different micrometers, but the length formula for any micrometer is as follows. Now I explained to you a similar concept in the video on vernier caliper also. So as in the vernier caliper, the total observed reading for any micrometer, using the total observed reading for any object, when you are measuring the length of an object for using any micrometer, is equal to main scale reading plus the product of the circular scale divisions coinciding the baseline of main scale times the least count. So as I mentioned in the concept of baseline, the baseline is important in this concept. First, the baseline is important to find the coincidence of the main scale and the circular or the vernier or the auxiliary scale. Second, the baseline is also important to find out whether there is an error on the micrometer scale. So as in the vernier caliper, the observed reading is found by adding the main scale to the product of the circular scale times the least count. So there's a great analogy between the concepts of the vernier caliper and the micrometer screw gauge. So having said that the baseline is important to two things, I explained to you that the baseline is important first of all to find the coincidence. So I explained that in the last slide. So in this slide I will be explaining the second advantage of the baseline, which is the use of finding the errors in a micrometer. As in the case of a vernier caliper, there are two errors. There are only two errors that can be found in any micrometer. However, you can only find one type of error on a micrometer. That is, you can find either the positive zero error or the negative zero error, but not both. So, positive zero error of a micrometer happens when the zero of the circular or auxiliary scale places below the zero of the meter scale reading. So you can see in this diagram that now if there is no error, if there is no zero error, this zero mark and this zero marks should coincide. So that's the use of this baseline. So this is the baseline, this small part here. So this is the main scale, this rectangular position, rectangular shape is the main scale. So this is the baseline. So this is the zero of the main scale. This is the zero of the vernier or the circular or the auxiliary scale. So if there is no error, this zero of the vernier scale and this zero of the main scale should coincide. However, in the case of a positive zero error, what actually happens is that the zero is placed below the main scale reading, placed below. In contrary, the negative zero error happens when the zero of the auxiliary scale places above the zero of the meter scale reading. Now here you can see that the zero is below, and in contrast, in the negative zero error, this baseline, the zero of the main scale is above the main scale or the zero of the meter scale. So those are the two errors in a micrometer reading. And as I mentioned, if there is no error or no zero error, the precise measurement for precise arrangement of the meter scale reading and the circular reading will be as follows. So this is the option where there is no zero error, and this is the positive zero error. So in the case of a positive zero error, you have to add this. But in the case of a vernier caliper, what we had to do is that if there's a positive error, we had to subtract it. However, you know that these two parts are still not met. These two parts are still not met. So what we have to do is we have to add these two parts. So in any micrometer in which it has a positive zero error, we have to add that error, and in the negative error we have to subtract that error. So how to take a measurement using a micrometer? So as in the case of a vernier caliper, the first step you would be to find whether there is an error on the micrometer. If the micrometer is of no zero error, or if there is no error of the micrometer, you can directly proceed to the second step. So the second step, as in the case of a vernier caliper, is to find the least count using the pitch. You can find the pitch and you can then find the least count. And as in the case of a vernier caliper, what you have to do is that you have to move away the rachet and place the object. Now we have to rotate the rachet. You can rotate the rachet here. You can rotate the rachet here so that the spindle goes in this direction. You can place the object here so that one part of the object, one surface of the object touches with the anvil, and then you can move the rachet so that the spindle firmly touches the other end or the other part of that object. So that is the second step. So the fourth step, so actually that's the third step. So the fourth step is to find. Now you need to know that whether this is actually accurate. As in contrast to the theory that you learned under vernier caliper, I explained to you at the beginning that there is no too much pressure exerted on the object when you are using a micrometer screw gauge. However, although there is no pressure exerted on the object, you need to see whether the object is firmly touched or it is loosely touched. That's very important when you are finding the width or the length of an object. If it is not firmly touched, the reading that you get, although your reading may be 100% correct, if there's error or no error, you can subtract or add that. Your reading, depending on whether there's an error or there's no error, it may be 100% correct. However, you may not get the expected result because there's no firm touch here. Because there's no pressure, you need to find out whether there's a firm touch. So what we do here is that we rotate the thimble, we rotate the rachet and we keep the object, and when we are satisfied thinking that the object is firmly kept, what we do is that we rotate the thimble until 3 clicks are heard. 3 clicks are heard. You can see, you can hear that when you are using an actual micrometer screw gauge. You can firmly keep the object, you can rotate the rachet and you can keep the object, and then you can rotate the thimble so that it is firmly touched, so that there will be 3 clicks heard. So that is the general procedure that we undergo when we are taking measurements using a micrometer screw gauge. So the next step, the fifth step, would be to find the main scale reading. However, unlike in the case of a vernier caliper, now one scale, that is a meter scale, is marked horizontally, and the vernier scale or the circular or the auxiliary scale is marked vertically. That's what I mean. What I mean by those two statements is that those two scales, the meter scale and the vernier scale, are actually in 2 dimensions. Unlike in the case of a vernier caliper in which both the scales are horizontal, we need to find out whether there is a hidden 0.5 millimeter, because you know that one part of a micrometer here, like this, for take the example here, this one part is equal to 1 millimeter. If this part is 1 millimeter, the parts between these two parts is half a millimeter. So this is 0 millimeters, 0.5 millimeters, 1 millimeter, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5, like that. You can go like that. So the scales on the meter scale, the lines marked on the lines marked above the baseline of 1 millimeter, and the lines marked below the baseline of 0.5 millimeter. So in the case when you are rotating the ratchet, the thimble rotates, and in this case you can see that the 0.5 mark is not clearly visible, but in contrast you can see that here you have to mark, or you have to take into account this 0.5 mark as well. Now consider these two positions. Now if this 0.5 mark is not visible, you don't have to add that to the final measurement. However, if you have the 0.5 mark visible here, or the line, the small line below the baseline visible here, you have to add that as well. So that's important in taking the main scale reading. So as the sixth step, as in the case of a vernier caliper, in a micrometer you have to measure the length, or actually the line that coincides with the baseline. So here you can see that here 35, 36, 37, here 38. So 38 is the line that coincides with the baseline. Here you can see is 20, 21, 22. So 22 is the line that coincides with the baseline. So that's actually the circular scale reading, and using the formula that we underwent in the last slide, what you have to do is that you can say that the final reading is equal to the main scale reading plus the product of the vernier scale reading, or the circular or the auxiliary scale reading, times the least count. So as an example, if you take a measurement like this, you can say that the main scale reading would be, here will be 5, 6, 7, and since this 0.5 mark is not visible, you can say that you don't have to take that into account. So the total measurement that you can take from the main scale reading is 0.7, and you have to add the product of the vernier scale reading, or the circular or the auxiliary scale reading, times the least count. So assume that the least count is 0.01 for both these measurements. So here is 35, 36, 37 and 38 is the line that coincides with the baseline. So you have to multiply 38 by 0.01, which is the least count, and finally you get 0.738 centimeters, or 73.8 millimeters. Here, now I explained to you, as in one of the previous points that I explained on taking the measurements, that here that if you have the 0.5 mark visible, you have to take that into account as well. So the total main scale reading now is not 0.7, because you can say here 0, 1, 2, 3, 4, 5, 6, 7. So 7 millimeters is actually 0.7 centimeters. So since this 0.5 mark is visible, 0.5 millimeters is equal to 0.05 centimeters. You have to add that as well, because here it was not visible, we didn't add that, but here since it is visible, we have to add this as well. Plus we have to take into account the product of the circular or the vernier or the auxiliary scale times the least count. So let's take the same least count as here, and the line that coincides with the baseline is 20, 21 and 22 here. So that will be 22 times 0.01, and when you solve that you will get 77.2 millimeters, or 0.772 centimeters. So those are two example measurements that you can take using the micrometer screw gauge. So in this video I explained to you about the introduction to micrometer screw gauge, what is the micrometer screw gauge, why micrometer screw gauge is important, about the parts of the micrometer screw gauge, errors of a micrometer screw gauge, special definitions, and about taking measurements. So in the next video I'll be going through some examples and the concept of the spirometer. So thanks for watching this video, and see you then.